Zhang, and it's about the transformers. And this project was a spin-off from the work I did with Dan Roberts, who is usually in Boston, but now in the Bay today. He wanted to avoid me for some reason. And then Boris time here. We spent 2 years working on this, but then the work I'm going to present is a spin-off from this. And this also is a sub-branch of physics of machine learning that probably oil one fraction of us work together. So hello? Should I speak again, or was I loud enough? Okay. So many of us work on physics of machine learning, and then the effective theory is one branch that I think is kind of fun for us. So I'm going to talk about that application of that transformers. And I want to begin this talk with very vague philosophical observation or motivations for why we do this. And one good example is like steam engine, which a few centuries ago, before we were born, it was leading to many wonderful things, like it lets you travel across the continent, but people didn't understand how this works precisely, and this was the black box at the time. But over time, we know that the thermodynamics and statistical mechanics were invented to explain what's happening in a steam engine, and that led to many more wonderful things. So right now, a few centuries later, we have this deep learning, which is obviously transforming the way we live, and hopefully in a wonderful way. And the hope is that by trying to fill out in the middle, we learn something new. At least that's the spirit. Okay, so this talk will be pretty short and hopefully simple, and outlines pretty simple. So first, I'm going to talk about simplification at scale, meaning that when you have a large network, as Chen just described, there are many simplifications that happen. So I'm going to just quickly review that, and then I'm going to dive into how this could be used for training transformer more efficiently. And please ask questions in the middle, don't wait until the last 10 minutes. Okay, so nowadays the neural networks are pretty wide, meaning that there are like many neurons in a given hidden layers, and these layers are stacked on top of each other many times. So that's like wide and deep. And in that limit, we now know that many simplification happens, as Chen just described, and many people in this room worked on. And I'm not going to talk about that, but then the one sentence summary is that there are simplification when there are infinite many neurons in hidden layers, as Chen just described. And basically, the law of large number kicks in, and there you have free theory at infinite width, so Gaussian processes and such Target kernels. But then like you don't have infinite networks on your laptop because you have finite money. So you have to eventually back off that limit to describe what's happening in a real network. And to do so, as a physicist, we can use the technique of perturbation theory. And it turns out that when the width is much larger than depth, meaning that the aspect ratio of network is small enough, then you can do the control perturbation theory to describe what's happening. Okay. So, and then you can actually have this effective theory language apply sufficiently modified to describe the real neural network. And the message is that when the width and depth is large enough, and when this aspect ratio or some generalization thereof is small enough, then you can have this effective description, whether in the limit being Gaussian or you have non-Gaussian processes and such. So, unfortunately for us, this is actually the typical large-scale setups. Like nowadays, the transformer has like tens of thousands of neurons in each hidden layer, and you have like hundreds of layers. So, but then the aspect ratio tends to be not too big. So we are in the right regime. We have a theory that can describe the real network that people use. Okay, And this has occupied me and Dan and Boris for the past few years, and of course many others. If I'm giving a talk on this, I'm going to review all the work, but then I'm not, so I want to say that many people worked on this and move on. So this was what I call physics of wide and deep neural network, but then I'm going to talk about the applied physics of it, or the application of the theory to the real network. So one thing you learn by trying to study this effective theory is that in trying to take the sensible limit of large network, you find some insight into like how you should scale the initialization of hyperparameters, meaning like how you should initialize the weights, and also like how you should scale the training hyperparameters like learning rates for each layers, and you can apply this in a real setup. And so hopefully by doing this, you can bring the theory and practice closer together at large scale. And so the particular work I'm going to present today is the one with Emily Dinan and Susan Zhang, as I mentioned. And I'm going to just take a transformers and apply this formalism and try to see how you should set up these hyperparameters. But the more global message is that given any network, I think this theory can be applied. And our paper was just one example where we work out in detail like all the calculations so that people coming up with a new network can apply our formalism to better engineer the new systems. And hopefully, like by knowing how to scale hyperparameter, you won't miss the discovery, because if you have a right idea, but then you don't know how to tune hyperparameters, you might miss something. But hopefully, knowing the theory, you can have more discoveries. Okay. So since people have short attentions, I have TLDR. And so 2 points. So one is that there's a principle of criticality, meaning that you should have every pre-activation and activation, so those dots that changes had should have order 1 numbers, meaning that they shouldn't be not too big, or they shouldn't be too big or too small. So like if like every pre-activation is like millions, then that's like kind of screwed up. And if it's like 0.001, then that's bad too. So it should stay in the range of order 1. And by doing some calculations, then it basically gives you the scaling for how you should set the initialization hyperparameter, or the standard deviation of each weight initialization should be square root of 1 over fan-in, where fan-in, so here, for those of you, I think many people know what fan-in and fan-out means, but then in case you don't know, so there's weights connecting 2 layers, and number of signal coming in is called fan-in, and then number coming out is fan-out. So usually you have fan-in by fan-out weight matrix connecting the layers. Okay, so standard deviation should be 1 over fan-in, and the intuition for that comes from usual random walk or central limit theorem. The second message is that there's a principle of equivalence, meaning that every layer should contribute equally to the learning. And that seems like a very vague statement, but then you can make use of neural tangent kernel to make it precise, that every layer contributes equally to the neural tangent kernel. And that gives you the insight that the learning rate should be scaled as 1 over fan-in for SGD. And if you're using Atom, then you actually have modified neural tangent kernel. So you have this modification by square root of fan-out. That's and then nowadays to train transformers, people use Atom W. So you need to know which optimizer you're using, and each optimizer people come up with, which maybe Joshua will describe. Then we can, for each one, you can work out how you should scale them. Okay. There are 3 caveats I want to mention. First one, caveat 1, we need to be careful with fan-in for sparse inputs, and I'm going to describe one specific example that comes up in transformers. And caveat 2, in transformers, there's like something called weight tying, and then that complicates things, but then we can work it out. Caveat 3, so in this slide, I put meta in parentheses for a reason. And when usually, so here we have only put the proportionality sign, or actually it's a similar sign. but to be more precise, you can actually fine-tune those factor of order 1, and that's a sensible thing to do. But then actually in a current setup, like people tend to insert layer norm everywhere, and then that tend to make that question kind of moot. So I'm not gonna talk about that today. But anyhow, that's a caveat. And one more caveat is that what I've described in the previous slide assumes that it's a neurotangent, what's called neurotangent scaling strategy. And there are different way of scaling up the hyperparameters for large networks proposed, and the most famous one in addition to neurotangent kernel is this thing called maximal update or mean field scaling strategy. Greg Yang and Edward Fu worked out for the deep network, and there's actually like even the one parameter worth of interpolation between those parameterization. But I'm not gonna talk about that. You can look at this paper that nobody cares, or we have sprinkled many footnotes in the paper in our in the paper I'm presenting. Anyway, so that's the first part. Any question? Can I see the time? Because I don't. Oh, sorry. Oh no, I just meant I don't see the. Cool. All right. So I'm gonna sure.
On the last slide, just so I want to have in the back of my mind, like what are the types of things that I should be thinking about? Should I be thinking about that if I do this different scaling, that the type of field theory I'm going to be getting is different, or that it's a totally different structure, or just a minor tweak? Should I be worried about this meta caveat, or can I just forget it for the purpose of this talk?
So for the purpose of this talk, you can forget it. But then I should mention, because you're a field theorist, is that one thing that comes up with this analysis is that actually this mu parameterization is an intrinsically strong couple theory. So for the neurotangent one, if you take a large risk limit, then you can you approach a free theory, and you can do the perturbation theory on it. And in this one parameter, so there's neurotangent maximum update and then interpolation between them. Anything B except the maximum update, if you take the width to infinite limit, then it always becomes free. But this one doesn't become free. And so you can kind of view, and then you can actually cook up or see what the so for neurotangent kernel, the perturbation parameter was depth over width, and then it becomes depth between, it becomes depth over some n to width to 1 minus s, and then as s goes to 1, then it becomes just depth. So it's never small. So that's how it happens. Kind of cool, I think, but nobody. Well, anyway. Okay. So the hyperscaling strategy for transformers. And for some, I'm going to just say that the bias and elements are affine parameters are turned off, just for the simplicity. And this slide should make no sense, but then it's just like you do a bunch of calculation, and then you get this main equation, which is basically summarized by that standard deviation should be 1 over phi n. And I'm going to walk through each block or each layers of your transformers to unpack what they are. And similarly, you have one more sets of equations for learning rate, and I'm going to unpack those too. And that's basically the rest of the talk, except that I'm going to present the experimental result at the end, very end. So if you know transformers, then this hopefully will be a way to get the more flavor of what I mean by those TLDR I presented. And even if you don't know transformers, then the purpose of this part of the talk is just to give you a flavor. And to go beyond flavor, you always have to just sit and read and do calculation on your own. So anyhow, so these are two main equations. Standard deviation should be 1 over phi n over square root of 1 over phi n. And I'm going to focus on atom W. So learning rate should be scaled as such and such. So since I'm talking about transformers, I'm going to go first with the attention block. So basically, there's Curie key value matrices, which are like n by n matrices, and N here is called embedding dimensions, just because you're basically embedding all the tokens into a vector space, and that's a dimensional vector space. And carry and key and value matrices work on these vectors. So here, these weights can have a same fan in and fan out, namely embedding dimension, which is the width of the transformers. And there's some caveats that you don't have to read. This is just hedging. And then if you plug this into that formula up above, then standard deviation is square root of 1 over embedding dimension, which is pretty much well known to be a sensible thing to do. The learning rate should be 1 over square root of 1 over embedding dimension to the cube. And that's just because if you plug that embedding dimension into that, then there's factor of embedding dimension times square root of embedding dimension, so you have cube inside the square root. So far so good. Even at 10 a.m. we can do this. One thing, if you know the transformers, one comment I want to make is that there's this famous factor of 1 over C for query key dot product. And here, C is the number of channels per head, and then that is defined as embedding dimension divided by number of heads. And this was in the original Attention is All You Need papers. And actually, the footnote has the right intuition. This is a random walk, so you should divide by 1 over square root of that. And then you can do the more esoteric calculation to just confirm that such a simple intuition, and then we do that in the paper. But the reason I highlight this, one more reason I highlight this is that, okay, so this is theoretically correct, but Tensor Program 5 paper does something else, so you should be careful with that. They do 1 over C, not the square root, and on the intuition that the query and key matrices will align, but I don't know how true that is. Please let me know if you know. I think nobody knows. Okay, let me move on. So there's in transformers, there's attention block, and then there's usual multi-layer perception or fully connected network blocks. And so this is the second main object, and this is usually 2-layer network, and you have embedding dimension going to actually larger space, m times embedding dimension, and then that coming back into embedding dimension. So for the first layer, fan-in is embedding dimension to fan-out m times m embedding, and then for the second layer, the reverse. And you just plug this in, you get this 1 over square root embedding dimension, and if you don't care about the m, then you have this cube appearing again. So basically, that's that. Okay. Usually people keep m to be 4, but then the reason I included m is that in the future, some of you might scale m to large, and in which case you should be careful and look back this talk, and you should be saved. Okay, and then so that's the main building blocks of transformers: the attention block and the multi-layer perception block. But then there are things at the head, at the beginning and at the end that you have to do, and one of them is word embedding. So you take a token, which is constructed as a number of vocabulary space vectors. So like say vocabulary number is like 60,000, and then you have that connecting into the embedding dimension. So naively, you might say that the fan-in should be this number of vocabulary, and then the fan-out should be embedding dimension. But that's incorrect. So you can do a bunch of calculation, but then to show that it's incorrect. But the intuition just is that usually each token is given as one hot vector. So only one component of the vector is non-zero, and everything else is 0. So basically, there's only one meaningful signal. So in this case, fan-in should be 1. So with that cautionary remark, you plug this in, and you get standard deviation should be order 1, and learning rate should be 1 over embedding dimension. And there are 2 takeaway from this slide. So one is that you should be very mindful with sparse features, not only for transformers, but then if you have any network that deal with sparse features, you should always be careful with what finding means. And the lesson 2 is that you notice that the learning rate so far up to this slide has been embedding dimension to the cube inside the square root, but then here there's no cube. So effectively, compared to the other layers, learning rate for this layer should be much higher. And then even if the network has embedding dimension only 1,000, learning rate for this should be 1,000 times bigger than other layer. And then you should, I'll show some experiment where taking this into account helps stabilize the training a little bit. So that's that. And also, this was caveat 2 I mentioned in the beginning slide. So here, so don't worry if you don't know the details, but then usually you have what embedding and then what unembedding at the end, and where you have a bunch of last features multiplied by weights, what embedding weights, which already we have set to be order 1. So, and you're adding up like embedding dimension worth of them. So, which means that this will scale like square root of embedding dimension, which is large. So you should divide the logits or the last output by such factor. Okay. And finally, quickly for positional embedding dimension, which is like a bias thing. And sometimes people don't use this anymore, but then they use something else for rope. But here it's like a bias finding is 1, embedding dimension is found out is embedding dimension. So again, learning rate should be much higher for embedding layers like this. Okay. So this was what I unpacked from this and that. So the question in the last 10 minutes, oh, I have so much more, okay. Does it work? Like, does it really help to have these theoretical insights? But before going to the experiments, is there any questions? Yeah.
So the answer, I say yes, no question, and answer is probably yes. But in the language of ABC parameterization, in this work, you only used A and C, right? But you still could use the gauge freedom to transfer like the learning rate scaling to some factor outside of the weight distribution.
Yeah, I don't remember A and B and C on the top of my head, but I'm pretty sure you're right. And then you can use gauge equivalence to like do the parameterization like changes did, or I did something else in my code.
So transformers don't have an issue with
Oh yeah. So you can generalize that. Yeah, basically, if you know find in and find out, then like you can work out the same kind of thing. Right, and then yeah.
Thanks, great talk. So you introduced one parameter M, and it was not clear M. Yeah, it was not clear why you need to introduce the parameter M there in the learning rate as well. And secondly, if you do not use learning, instead just without learning, just see what the output of the transformer is, we still see some signs of optimization there.
Sorry.
So
let me answer the first question because I tend to forget if you ask the question. Okay, so here, right? Okay, so to answer that question, so M is in a definition of it, and people use it. But here, the reason is that the fan out scales like M. So if you plug that into that formula, then M comes out. So just plugging in, and then I'm pretending that M is a large number here, just for the future.
Okay.
But if you fix M to be 4, then it may not matter too much, and it kind of get confounded with the fact that you can also tune this 1.0 to something else. But
I see. So you're setting yourself up for a 1/m sort of expansion ahead of time.
Yeah. So everything is 1/n embedding dimension. Actually, to be more precise, it turns out to be 1/channel expansion. that's the leading contribution. Like that turned out to be the 1 over C turned out to be the expansion parameter if you work out, and the intuition is that every head is working like a tiny network, and then there it's 1 over C that matters. And what was the second question then?
Sure, thanks. This really helps because second question was if we don't train, then the learning rate will not play its role, but the other normalization factors that you have included, say in the standard deviations, they are still going to show up in any kind of expansions that you do.
Yeah, yeah. So right. So if you want to do some, say, Bayesian, then and again, even there, this 1 over C is the expansion parameter, and then you can, if you fix everything else and then put the embedding dimension to infinity, then you get the infinite, the kernel limit, and such and such. Everything. So I think this. I wanted to just globally, what I wanted to say was that we've developed this formalism as a community to deal with the MLP, but then MLP people don't use much. But then once you work out for MLP, it's not so hard actually to apply it to things like transformers. You just need to attend to a few things as expansion parameters, and then from there just spending a week of fun calculations.
Makes sense. Thank you.
Right. So I mean,
sorry, Sho, could you? There was a discussion in the last talk about how the size of the data enters. Would you comment on that as well?
I want to. Yeah. So right. So this is kind of independent from the transformer itself. It's a general question of when does the perturbation theory breaks down, and I think, well, didn't we? Okay. I thought we talked about this personally, but maybe I'm not remembering. So okay. Anyway. So there's part of the correction. I said that it's proportional to the depth over width, but then there's also the question of how each term scales with data set size, and naively looking at the number of indices that's summed up for these perturbation corrections, you naively think that it's going to break down quickly because the perturbation correction scales much more quickly than the kernel object. But there's a counter argument to that, which is that when you have a structured data, then maybe this each time plateaus when you take a large data limit. So, but that's a question that I hope to know how to tackle, but I don't know at the current moment. So I have only 3 more minutes, which is cool. So I am gonna just do experimental things. So the question is, so okay, you can do the theory, but then does it work in practice? If it doesn't, then it's useless. But I hope to say that it's useful, good news for us. And here, the experiment we did is for Bijon transformers, and the black line and the gray. So we did 3 Cs for each kind of parameterization. And right now, the black and gray, 2 gray lines are for a usual standard parameterization, meaning that you don't care about the fan in and fan out. You just put the learning rate to be same for all the parameters, which is the usual standard practice, which people should abandon at this point. And for this setup, it turns out that this is very unstable. Like you have a bunch of spikes appearing, and that's pretty bad. And then you observe, like in a large-scale experiment all the time, there's a bunch of spikes, and then that's problematic. In this instance, it seems like the correct parameterization cures. I'm not going to generalize this statement to others, but at least in this one instance, for example, if you look at the blue curves, which is the neural tangent parameterization, then it's just smooth and actually performs a little bit better than the standard parameterization. And we've also actually tried maximal update parameterization, and which is red, and it's actually in this setup worse than the standard parameterization. And then we also tried the hybrid, which is, so I talked about this interpolation, and neural tangent kernel is blue, maximum update is red, and then I did the half point, which is hybrid, and it seems to work best in this setup. But I'm not going to claim that this is, I suspect that this is task dependent, and then depending on the task, I don't know which parameterization you should want to, which parameterization strategy you want to employ, and hopefully more people do experiment in a different setup, and then you have more ideas about when you should use what. Okay, so here it seems to work well here, right? And one curious observation, which is that so if you plug in a bunch of numbers with this optimal hyperparameter and such, what neural tangent scaling is doing with respect to standard parameterization is actually increasing the learning rate for positional embedding and positional embedding by a factor of 1,000, which seems to intuitively instabilize the training, but actually in this case stabilize the training, which is interesting thing to observe. And so intuition I have is that you actually should want to balance the gradient from each layer. If you don't, then some layers lag in training and it makes things unstable, but that's just a posteriori explanation of what happened.
Can I ask a quick question?
Sure.
Right.
Yeah.
It seems like in this plot, everything converges to the same point.
Also, you have to zoom into the last point. So these numbers at the end in a legend is accuracy.
Okay.
So, but it's a tiny difference.
Okay.
Sometimes people care, sometimes people don't.
Is there like annealing or something? Is there a reason why these spikes disappear eventually?
Oh.
Can you speak to that?
Sorry. So I'm doing the linear warm up to that dashed line, and then doing the cosine learning rate decay. So the noise will go down, but the accuracy at the end is different.
Thank you. And because of all the questions, feel free to continue the presentation. We have 15 minutes for questions, so you can use.
But I have two more slides only. So does it work? So we tried for the large language model in our setup R2C2. I don't know which movie they took it from, so we train R2C2 and also BART, and black is the loss that you want to lower, and so for BART it didn't matter, and the R2C2, which is larger, it seems like neural tangent kernel one was winning, but for various reasons we have to stop the training in the middle. I don't disclose why, and but this looked encouraging, but they're not conclusive. So I wouldn't dwell too much on this. But hopefully, some of you will do more experiments, and then we'll see. But hopefully, this learning rate scaling is sensible and interesting. So some of you try, and we start maybe from here, from someone in this room or someone hearing on the YouTube. Lots of encouraging or discouraging anecdata will come from you, and hopefully we'll sort it out as a community. Thank you very much.
All right, already have a lot of questions.
It's a great talk, thank you. Do you have any intuition for why the scaling for the learning rate for SGD is different from Atom?
Oh yeah, it's just a calculation. So basically what happens is that the atom have this second moment in the denominator. So let me go back. And you have square root of second moments. And if you calculate what each component of gradient is, and you do the back of envelope calculation, and you estimate what the order of magnitude estimate is, and it turns out that each gradient is 1 over fan out. So you have to compensate for that, and that goes into that fan out upstairs. But I guess I should go back to. Oh yeah, here. Right. But for each optimizer, basically what you do is that you can actually. So in our paper, we did all the calculation, like everything. But then, like in the back of your head, when you're drunk, what you can do is that you can basically remember like what the each magnitude of each component is, and then look at the optimizer algorithm, and then you can adjust for it.
So my question is regarding the experiments. So you have mu-p experiments, and you're comparing with neural tangent and comparison of neural tangent and mu-p experiments, right? So
only for vision transformer.
But you said that for neural tangents you get a higher learning rate, which was order of 20, because you scale the embedding layer differently. Is that correct?
Right. So I should say that to be fair comparison, for each parameterization, we swept learning rate and weight decay and made sure that in a log2 grid, like it's the optimal choice for each one. And after doing so, the neural tangent kernel and standard one is so learning rate is 0.001 for standard, neural tangent is 20. It was optimal. But that difference actually is for most of the model parameters like query and key matrices. If you factor in this one over fun in with like finding 1,000, then it kind of comes out right to be equal learning rate. Meanwhile, for the embedding, positional embedding, like it turns out that it's 1,000 times bigger learning rate, and so yeah, and then that's more stable somehow.
Hi, Sho. Great talk. So when I look at this plot, I'm actually just honestly forgetting the different names. Which one is the line associated with your analysis?
I mean, our analysis applies to any parameterization. So you mean in a paper or in a talk? In a talk, I basically presented neural tangent one, so blue.
Okay.
But then in a footnote of the paper, we do say what you should modify to get to the maximum update or interpolation between them. So that's, yeah.
I see. And do you have a sense, part of the point of maximal update is about how the optimal hyperparameters scale as you scale up the system size. Did you do such an analysis in this case? How the optimal hyperparameters scale as you scale up the system size? You know, Greg and company wanted to sort of stay fixed.
I think so. To be fair, like neural tangent one is also a sensible way of scaling the hyperparameters. Like they compare only standard and maximum update, and they somehow employ only maximum update. But I think to be fair, every parameterization strategy is sensible within this parameter family. And I think the jury is still out. Is that how you say?
The jury is still out.
Yeah. So, which one is better for which task and such?
One final question. When I look at this,
although I should also mention that the Tensor Program 5 paper is maximum update plus that one strange way of scaling the dot product.
The C parameter. This one over C.
So you should be careful with that. But yeah.
When I look at this plot, the first takeaway that I see, I mean, they sort of all converge to the same thing, but actually maximal update learning kicks in at late times as compared to the others. Do you have a sense of why that is? Is there some intuition?
I guess I'm pausing, so I don't think I have any. No.
Thanks.
So for all these scaling analyses, there's a dependence, of course, on the architecture, and in certain special cases, with sparse data, there's a dependence on the inputs. But there doesn't seem to be dependence on the problem that you're trying to solve, or the choice of loss function. Is there an intuition for why that doesn't play a role in this, or maybe just because we end up having problems that are all very similar in nature? Is there any place where the problem specification might come into play in terms of scaling behavior or limits?
I mean, that was like double-edged sword sort of thing. Like in a sense that it's nice that it's universal. Like you don't have to look at the program to see how you should scale, but you're also not getting some insight into what the program is but one thing that could happen is that when you back off from that limit, the infinite risk limit, then that kind of difference might show up. But I'm kind of waving hands and like, saying random things. Yeah, so the program dependence. Yeah, I'm not sure. The optimizer dependence, I kind of said that the SGD atom, but yeah, one thing that was hard to incorporate into the effective theory was that we basically always condition on a given data set, and meaning data set and task, right? And then you can work out the theory and such, but how to so you kind of have already a shredding equation, but then now incorporating the data structure into the theory is, I think, largely open question. There are some work like Alex Maloney, James Sully, and Senjis, and like Kantor, like I think Dan and everyone. But yeah, I think it's a wild open field. How should you make a toy model for the data sets, or should you be able to extract something real about the real data set? Yeah, I don't.
Yeah, let me ask my question in a different way. Is the task independence that seems to show up in the formalism, is that something that you think is generically true? Or is that a limitation of the formalism?
For the thing I said, I think it's true statement, universal statement, at least like, because you can work out everything with the caveat that you should always be careful with like sparse features and such, sparse inputs and such, but that's except at that input level and maybe output level, inside the network, it's pretty universal. Because, yeah, statement is pretty universal. Everything should be order 1, and then it just comes out.
Any last questions? Right, there's 2. Not sure who went first.
Can do 2.
Thanks, Sho. That's a really interesting talk. Just to follow up maybe on Jesse's question, it seems like you still have order 1 parameters you have to tune even when you know how things scale with respect to the architecture. And so, it's possible that when you do your hyperparameter search over like the weight decay coefficient and other order 1 numbers, like that's going to be task dependent. Right.
Sure,
and when we don't really understand, I think largely how that works, we just kind of search for them. So maybe that's like a partial, place where one could try to understand more about the data and maybe have even more insight about how to set those kind of.
I mean, like, yeah, the eigenvalue kind of encodes something about the data structure, and that encodes like what the learning rate should be, or the what the range of learning rate should be. Yeah, so I don't know how the output comes in there, but.
Well, question for future research.
Can you say a little bit about what you mean that by saying that your like formalism also applies to maximal update parameterization? Because like I saw that you had some scaling of like how learning rate should scale with fan in and fan out, and maximal update has.
Yeah. So I can. So there's an interpolation S that S equals 0 is near tangent, S equals 1 is maximal update, and then you can. I don't remember on top of my head like how you should, but then we put in a footnote like how you should scale with this scaling, how scaling should change when you change this S interpolation parameter. Does that answer your question?
But did the S appear in the talk?
Oh no, I.
Okay.
Even paper, like it's in footnotes, so in the talk it doesn't appear.
Thank you.
Right.
There's 1 minute left. I guess I'll ask the last question. So I think Greg Yang would probably say that MUPI is the only way that you can have like non-trivial learning at large scales or something.
Right.
And I was going to ask you to comment on that.
Yeah. So I think what Greg says is true if you fix the depth and send it to infinity. So the part of the reason why, so I put out this paper that I said many times that nobody cares, I didn't want to publish this, but the one reason I wanted to emphasize, well, some people encourage, like Surya encouraged me to write this up. I don't know whether he read it or not, but anyway. So the one thing I wanted to emphasize is that the perturbation parameter comes out to be depth over width to some power, as I was saying to Jesse. And if you look at just that number, to keep that order 1 in a limit, then what you can do is that if you're sending only width to infinity, then the Greg's parameterization is the only one, but that's wide learning. And but in general, so let's take NDK parameterization. And what you can do is, what you see is that what you can do to keep future learning in a limit is to grow the network while keeping the aspect ratio constant. And then for each scaling strategy, you have something to keep it fixed, to keep the future learning in a limit. So no, it's not the only one. The only one only if you keep the depths fixed.
Okay, thank you. All right, let's thank Sho once again.